Welding transformer output power. In this example we have a simple single-phase transformer. This transformer is of the old type used for the welding applications. In transformer we have the core, the primary winding and the secondary winding connected to the variable load. The load includes 1 picofarad capacitor and the variable resistor. Primary winding is connected to the AC voltage, frequency 60 Hz, and our task is to calculate the output voltage as a function of loading current. Let's start QuickField now. In QuickField I create new problem. Problem name transformer. Next. Problem type is AC magnetics. Frequency is 60 Hz. Model class is plain parallel. The core thickness is 50 millimeters. Length units are millimeters. To simulate the problem I will need to draw the geometry model, provide material data, and I will need the electric circuit to specify the connection. So I type in the circuit file name here. Circuit 1. Finish. On the left you can see the problem pane, and on the right you can see the geometry model editor window. Here you can draw the geometry model, or you can import the geometry model from an AutoCAD DXF file. DXF file is used by the majority of the CAD programs to interchange two-dimensional geometric models. I already have the geometry model prepared, so I will import the file. Here you can see the geometry model was imported. We have the core, primary winding, secondary winding, but some elements are missing here. In fact, magnetic field is distributed not only in the core, but also in the air outside, so I need to add the air. Switch to insert mode, zoom out, again, change the line type to half arc, and draw the outer boundary. Now this would be the air. The geometry model is ready. Now we should assign labels. For labels we will specify material properties. Switch to select objects mode. Click the object to select. Open the properties and type in the label name. This would be the air. You see the label appeared in the tree. Again I click and select the block. This would be the core. Okay. Now let's zoom in to select the windings. Switch the zooming mode off. Click here. This is the air. Now I will use the rubber band to select multiple objects at the same time. This would be the insulation. Okay, and this would be secondary winding. Secondary plus. These blocks are secondary winding minus. And these blocks are secondary winding plus. Okay. Again, I need to zoom in to assign labels to the primary windings. Switch the zooming mode off. And again, I will use the rubber band to select multiple objects. These are primary plus. And these are primary plus. Now let's move inside the core. Hold the Ctrl button pressed to select multiple objects at the same time. So I select this portion, this portion, this one, and another one. These all blocks are primary minus. And again I move to the right. These blocks are primary plus. Okay, let's zoom to fit and check what we have in our model. We have the air, we have the core, the insulation and the windings. Now let's specify physical properties. Double click the label name in the tree, and in the properties dialog for the air I will specify material permeability, which is 1 and nothing else. Okay. The same for the insulation, magnetic permeability of 1. Okay. For the core I specified permeability, which is 1000. The core is eliminated, so I do not specify electrical conductivity. Okay. For the primary minus I specify magnetic permeability of copper, which is 1, electrical conductivity of copper, which is 56 megasiemens per meter, and that's all. I should not specify any source value here because we have the co-simulation with the electric circuit, and all conducting blocks from the model should be included in the circuit. Well, in fact the label primary is assigned to many conductors, so here I specify that these conductors are connected in series. This means that total current in each conductor will be the same. Okay. And the same for all other windings. Permeability, conductivity, conductors connection in series. Permeability, conductivity, conductors connection in series. Permeability, conductivity, conductors connection in series. Okay. That's all for the blocks labels, but we should also assign the label to the boundary. So I select the boundary and assign the label boundary. Far away from our transformer, magnetic field fades to 0, so at the external boundary I specify 0 magnetic potential. Okay. That's all for the geometry model and for material properties. I need only to build the finite element mesh, just press this button. Field simulation part is ready, but remember we have electric circuit. So I open the circuit and I should place all conducting blocks from the model in the circuit. These are primary minus, primary plus, secondary minus, secondary plus. Next I will add the voltage source. Select, double click. The voltage source root mean square value is 220 volts. In QuickField we should specify the magnitude, which is RMS value times square root of 2. Okay. The secondary is connected to the capacitor. The capacitance is 1 microfarad. Okay. And we have the resistor. The resistor initial value is 10 ohms. Okay. Now I will use the wire to connect the elements. So the electric circuit is ready. Now I should save all problem files and start the analysis. The problem has been solved in 4 minutes and we can take a look at the results now. Here you can see the magnetic field lines and the color map of the current density. You can adjust the field picture. For For example, I will switch off the field lines and switch on the color map of the flux density. Now let me check the flux density values in the core. I will use the probing tool, click in the core, and here is the flux density. There is another option to measure values. I will use the contour tool, draw the contour line here, and get the flux density distribution along this line on the XY plot. And you can see the field values in the table. Coordinates, flux density. Okay. I can also use contours to calculate integrals. Click the integral calculator, and here I can calculate the magnetic flux, and I can calculate the cross-section area. But my task here is to calculate the output voltage. So I switch to electric circuit simulation results. Here I can get the current and the voltage for any element. I can get to know the loading current in the primary winding. I can measure the current and the output voltage in the secondary winding. These values I will use to calculate the output characteristic of welding transformer. So next I will need to calculate the output voltage for another loading value. I should open the electric circuit, change the loading here, for example 5 ohms. Save all problem files and run the analysis again. 4 minutes later, and again I can take a look at the results. These are the field simulation part results, and I will switch on the electric circuit results. And here I can measure the current and the voltage. I can put the data in Excel and keep on working. In fact, there is a faster way to calculate this table. QuickField features the label mover tool for parametric analysis. The workflow is simple. I will use label mover in the serial analysis mode. I choose the base problem, which is transformer PBM, add the values to measure. I will measure the current and the voltage in the electric circuit element. Add the current, add the voltage, close. Here you can see in the values tab the current for the R1 and the voltage for the R1 appeared. Next I should specify which parameter to change in the problem setup. This is called steps. Record steps. I would like to change properties. I will change the resistance value. Increase by %. Okay, I will increase it by -50%. Add step. The step was added. Close. And I would like to repeat this step 10 times. Okay. Now press Get the Results button. A series of problems will be generated. In each problem, in the electric circuit data will be adjusted, the resistance value will be changed. Then the problem will be simulated and the current and voltage values will be calculated. All these steps are performed automatically. We can have a short break and return later when the results are calculated. On my computer I have the processor with 4 cores, so you can see that 4 problems are simulated in parallel. All problems have been simulated and you can see results here in the table. Current value and the voltage drop value. And if you switch to the plots of results tab, you will see the plot. Voltage versus current. You can save the script file. You can copy all the results. I will paste it here in the Excel file. And in Excel you can make the XY plot. Voltage versus current. If you search for the welding transformer on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting picture, and here you can download the simulation files. Simulation files may be viewed any QuickField edition, including QuickField Student Edition that you can download from our website for free.